Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, this hour is your hour. Let's take the first listener phone call.
Hi, this is Kathy in Charleston, South Carolina. I don't know which radio station I'm listening to due to Hurricane Matthew knocked out my Wi-Fi. I would have looked this up. But do we have, is there really such a thing as peak noise? And if it is, what's the difference between peak noise and white noise? Thank you.
Well, you ask a very interesting question. First of all, white noise. White noise is that shh sound that you get when you turn the volume all the way up, but there's nothing coming on. So you hear that shh sound, and that's called white noise. And what is white noise? Why can't you get rid of it? Believe it or not, it's caused by the random collisions of electrons inside your radio. That's right. You're actually looking at the random fluctuations, quantum fluctuations of atoms as they bounce around your hi-fi, your radio, your stereo, or whatever. And so some people say, well, when I turn up the volume on my radio or whatever, why do I have to get this white noise? Why can't I simply eliminate it? Well, it's hard to eliminate because you cannot eliminate the random collisions of electrons jostling around inside your radio. Now, you mentioned peak noise. That I don't quite understand. There's something called peak signal to noise. I think that's what you're asking, because there's really no such thing as peak noise that I'm aware of. And peak signal to noise is the ratio between the usable signal and the noise. And so you want to have a good signal to noise ratio, or else you'll just hear a lot of white noise wiping out what you're trying to listen to. And then the other question is, what about the static? The static that you sometimes hear that doesn't seem to be white noise at all. Believe it or not, a lot of that static comes from the planet Jupiter. That's right. You're actually tuning in to Jupiter. Jupiter is the most radioactive planet in the solar system. Our space probes have to be reinforced or else they'll short out as they get too close to the planet Jupiter because of all the radiation fields surrounding Jupiter. And so, yeah, a lot of that static that you hear when you go, let's say, between channels comes from Jupiter and also from Genesis, the Big Bang itself. It turns out the Big Bang created a tremendous wave of radiation that permeates the entire universe that you can actually detect with your radio. That's right. Your radio can actually detect remnants of Genesis. The Big Bang was so powerful that it generated a tremendous amount of microwave and radio radiation that is still circulating around the universe, and you can pick up some of it in the static you get when you're going between stations on your radio or your TV set. So the simple question of what is noise is actually rather revealing, and it really goes to the fabric of reality itself. Okay, well, let's move right along and take the next listener phone call.
Hi, I'm calling from Charleston, South Carolina, and I was wondering how the hologram theory and the string theory work together, or whether or not do you think they do work together, and what your thoughts are on the hologram theory.
Okay, well, you ask a pretty advanced question, so let's try to break it down into its components. First of all, string theory. String theory is actually what I do for a living. That's my day job. The city of New York pays me to work on string theory. And string theory, we think, is the theory of everything. Some of you may have seen that movie 2 years ago, The Theory of Everything, that won the Oscars. Well, the movie was great. I saw it. It's all about the life of my colleague, Stephen Hawking. However, it didn't tell you the name of the theory of everything. I was waiting for them to say, oh, by the way, the theory of everything has a name, and that name is string theory. In other words, string theory, we think, is, in some sense, the final theory. We have, on one hand, the theory of big things, and that's Einstein's theory of relativity. That gives us black holes. That gives us, well, the atomic bomb. It gives us the large-scale structure of the universe itself, Einstein's theory. theory of gravity. Then we have the theory of the very small, the bizarre theory called the quantum theory, that makes lasers possible, that makes electronics possible. You are hearing my voice as a consequence of the quantum theory. And so some people say, well, Professor, what has the quantum theory done for me lately? Huh? What about numero uno? Why should I believe in you quantum physicists when it doesn't affect my life? Well, quantum physics makes possible the transistor, which in turn makes possible the computer, which in turn makes possible the internet and iPhones and iPads and all the wonders that you take for granted, all of it coming from the quantum theory. Now, so nature has two theories, the theory of the big and the theory of the small. The problem is they don't talk to each other. They don't like each other. They are based on different mathematics, different assumptions. The only theory that can marry these two together is string theory. So string theory is based on vibrations, tiny little vibrations of a tiny little string. These are quantum vibrations. That's the basis of quantum mechanics, because what does quantum mean? Quantum means a packet of energy. And each vibration of a string is a packet of energy. So string theory, almost by definition, is a quantum theory. But when the string moves in space and time, it forces space and time to curl up just the way Einstein predicted. In fact, the first vibration of the string will reproduce all of Einstein's theory. So let's take a short break, and afterwards we'll talk about the holographic principle. Are we living in a hologram? Are you a hologram? We'll find out after we take the break.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're throwing the lines open. One of my friends works for Con Edison. He's an engineer that works actually at a nuclear power plant. And he was just shooting the breeze with other Con Ed workers. And one of them said, just out of the blue, if the sun were to disappear right now, how long would it take for us to notice it? If the sun were to disappear right now, what would happen? Well, everyone had an opinion. The problem was all the opinions disagreed with each other. Nobody could answer that question. Well, we haven't done this experiment, thank God. But according to modern physics, when the sun disappears right now, it'll take 8 minutes. 8 minutes for the Earth to be thrown out of its orbit because gravity takes time to move across space and time. Gravity, the disturbance of gravity comes in waves, and these gravity waves travel at the speed of light. So in other words, it's not instantaneous, as Newton thought. It takes 8 minutes for the Earth to be flung into outer space if the sun were to disappear right now. Okay, well, let's move right on. And before the break, we had a call about the hologram principle and string theory. What's the relationship? Well, string theory, as we said, is a real theory that gives you numbers. You can calculate with it. And it says that all the protons and neutrons and mesons that we see in our accelerator and all the quantum effects that we get with the internet and laser beams, all of it is due to tiny little vibrating strings. So each note of a string is a particle. That's why we have so many particles. The harmonies of the string gives you what is called physics. What is physics? Physics is nothing but the laws of harmony of vibrating strings. What is chemistry? Chemistry is nothing but the melodies you can play on interacting strings. What is the universe? The universe is a symphony of strings. And what is the mind of God? The mind of God that Albert Einstein worked so hard to read is cosmic music. Cosmic music resonating through 11-dimensional hyperspace. Now, what is the holographic principle? Well, what is a hologram? We see holograms, for example, at Disney World. And if you're into Disney World and you see those ghosts when you go through the ghost ride in the haunted house, these ghosts seem to come at you in 3 dimensions. That's a hologram. So what is a hologram? First of all, it's a flat sheet of glass. But on the glass, there is a plastic emulsion And that plastic emulsion has an interference pattern of a three-dimensional object. So you're taking a three-dimensional object, taking its waves, and flattening it out, and making an impression on a flat two-dimensional surface. So when you shine a laser beam through a flat two-dimensional surface, you see the wavefront of a three-dimensional object. And so in other words, the ghosts that you see at Disney World is an illusion. But it's three-dimensional because the light coming at you has all the information of three dimensions. So in other words, a three-dimensional world has been encoded on two dimensions. Believe it or not, a two-dimensional flat plane of glass has the information of a three-dimensional wavefront. Now, that's the holographic principle. Now, the question is the universe a hologram? So if you have a higher dimensional object, perhaps you can imprint it on a lower dimension. And so we think we live in three dimensions. We have length, width, and height. But perhaps we are encoded in a higher dimension. And so perhaps reality is really 4 or 5-dimensional, and we think we're 3-dimensional, but we're not really at all. And so in other words, the dimensionality of space and time is at stake. That what you think the dimensionality of the universe is not really what is happening. Now, as bizarre as this sounds, it is the basis of holograms, which can give us 3-dimensional television one day. And it's also the basis of string theory. String theory has within it a holographic principle. And so that's why the holographic idea has come back into fashion again. Because it turns out, and this was done at Princeton, that string theory does in fact allow you to encode a d-dimensional universe into a d plus 1-dimensional universe by flattening it out. And so string theory has gobbled up the holographic principle. Okay, well, let's move right along to the next listener phone call.
My name is Roberto Goffman, calling from Florida. I would like to know, why is there much resistance against string theory in the scientific community? And also, what is lacking from current understanding of string theory for it to be Einstein's quarter-inch equation that connects the quantum and the science of the very vague relativity? Thank you.
Well, you ask a very important but very embarrassing question. If string theory is so great that it has all the wondrous physics of everything encoded into a tiny little equation, then why don't we win the Nobel Prize? How come textbooks are not written for high school kids, introducing them to the basics of string theory? Well, there's a problem. You see, the energy at which you need to test the theory, to actually create these new particles, is far beyond what we can create with the Large Hadron Collider. First of all, the particles that are predicted by string theory, they're called sparticles. Sparticles are superparticles that obey something called supersymmetry, but we have never seen a sparticle. So some people say, yeah, so you think you're the successor to Einstein? Prove it. The proof is in the pudding. Where's the pudding? In other words, where's the beef? How do you prove a theory of everything? Well, there is a way to do it. The Large Hadron Collider discovered the Higgs boson recently, caused big headlines around the world. The next goal of the Large Hadron Collider, this huge atom smasher outside Geneva, Switzerland, the next goal is to create sparticles, superparticles, particles that we think make up dark matter. Now, dark matter, we do know exists. We actually have maps of dark matter. There's more dark matter than ordinary matter. So most of the universe is not basically made of atoms. Most of the universe is made out of an invisible substance called dark matter. What is dark matter? We know it exists. We have maps of it. It holds the galaxy together, but we don't know what it is. If you in the audience ever discover what dark matter really is, tell me first. And we can share the Nobel Prize together. Yes, you and me, you being the creator of this great idea, will share the Nobel Prize together. Well, the leading theory of what dark matter is its sparticles, a higher vibration of the string. Now, if that pans out, then, of course, string theory will become the center of all physics. But, hey, we haven't done it yet. The proof is in the pudding. We have to prove it using hardcore experiments, and that we don't have yet.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're once again throwing the lines open because this is your chance to get on national radio. Okay, well, moving right along, let's take the next listener phone call.
Hello, this is Armand, and I'm from Bayside, Queens. I was wondering, you said that plants have around a level 9 or 10 consciousness, and dogs have around a level 1 or 2 consciousness. What level of consciousness do we have, and what do you think plants experience? Do you think they experience pain? And that's it. I hope you have a great night, and thank you for everything.
Okay, yes, in my latest book, The Future of the Mind, I actually define consciousness and rank it numerically. Now, remember that in science, there's no consensus on what consciousness is or even a definition of consciousness. But I'm a physicist. We like to define things and then numerically rank them in order to test the theory. Otherwise, we're just philosophers. And so I define intelligence as the accumulation of evidence which allows us to create a model of who we are. A model of who we are with regards to space, that is our location, with regards to society, that is our rank in society, and also with regards to time. So, in other words, it's the constant accumulation of data that allows us to create a model of who we are. So, for example, take a look at a thermostat. I think that even a thermostat, even animals have consciousness. A thermostat has the smallest unit of consciousness because it has one feedback loop. It simply measures the temperature and adjusts the temperature around it. One unit of consciousness, the thermostat. A plant may have 10 units of consciousness. It has to know where the sunlight is. It has to know where the water is. It has to know the direction of gravity. It has to know when to shoot out leaves. So plants have several feedback mechanisms depending upon the weather, humidity, so on and so forth. So I'd say that plants have maybe 10 units of consciousness. Bugs have even more. Now, I call this level 0 consciousness. These objects don't move. They don't have much of a society. They just sit there like a plant. Now we have level 1. Now we get to animals. Level 1 consciousness is that of an alligator. That is, they understand their place in space. They understand where their prey is located. They understand where they are located. And much of their brain corresponds to helping them locate their position in space and the location of the prey so they can eat. That's level 1. Level 2 consciousness is that of a mouse or monkey. These are social animals. They have emotions. They have social hierarchies. They have a pecking order. That is much more complicated than that of a simple alligator, or, of course, much more complicated than that of a tulip or a plant. So they have emotions. They have social consciousness. Then who are we? Who are we? What separates us from the animals? Why are we different? We're just smarter? Well, what does that mean? I'm a physicist. How do you rank smartness? I say that we are different from the plants, different from the animals, because we understand time. We constantly run simulations of the future in time. Well, let's take a short commercial break, and after the break, I'm going to talk about what is a human mind and how does a human mind differ from that of a plant or animal, and do plants feel pain?
This is Science Fantastic.
Science Fantastic with Professor Michio Kaku. It's open mic on Science Fantastic. Well, before the break, we had a question. Do plants feel pain? How do you rank consciousness? What separates humans from the rest of the animal and plant kingdom? Well, first of all, are plants conscious or animals conscious? I think they are. In fact, I give you a numerical scale by which you can rank the amount of consciousness of a plant, an animal, and even a human being. 3 levels of consciousness. The first level allows you to understand your position in space, like an alligator, like a reptile. That's the back of your brain. The back of your brain governs your position in space, time. It's called the reptilian brain. It's the brain of a reptile that you have at the base of the back of your neck. As evolution progressed, the brain grew in the forward direction. So the middle of the brain is the limbic brain, the monkey brain, the brain of emotions, because the brain grew from back to front. In fact, that's how baby brains operate. When a baby is born, most of the brain is reptilian in the back, but the brain grows toward the front as the baby gets older. That mimics the stages of evolution. So the center of the brain is the limbic brain. That is the emotional brain, the monkey brain, the brain of social hierarchy. Then the front of the brain is the human brain, the prefrontal cortex. And what does it do? It simulates the future. It understands not just space, not just society, but time. It allows you to predict the future. Because when you daydream, what are you doing? You are constantly running simulations of the future. Gee, how do I get that date? Wow, what do I say to my boss? I mean, what am I going to do tomorrow? What's my goal in life? All these questions are about time. Now, let's do a science experiment. Go to your dog tonight, go to your cat tonight, and teach them the meaning of tomorrow. That's right. Teach your pets the meaning of tomorrow. And you'll find out you cannot. No matter how you try, you cannot convey to your pets the concept of tomorrow. The pets that you have very clearly understand space. They can fetch things. They know where things are located, like food. They're social animals. They know social hierarchy. They know who's top dog, bottom dog. But they don't understand time that well. Now, you may say to yourself, well, that's a bunch of nonsense. I mean, bears hibernate, don't they? Yeah, but that's instinct. They don't consciously say, oops, it's wintertime, I got to pack my clothes, I got to get ready for that trip to Florida. No, bears don't do anything like that. Bears simply say, ooh, it's cold, and they hibernate and fall asleep. It's automatic. And so that's what separates us from the animals. We simulate time. We simulate the future. We can see not just tomorrow, but we can see the day we die. We can even see beyond our death date. We can even look into the future beyond our own years. That's what separates us from the animals. Well, unfortunately, we have to take yet another short commercial break. But after the break, we'll talk about plants and do they feel pain.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. It's open mic. Before I take the next list for phone call, once again, let me answer that question about plants. Do they feel pain? Well, pain, as we understand it, plants do not feel. Plants have no nervous system by which they can sense the environment. They only sense the presence of water, the presence of, let's say, air, the direction of gravity, but not much more because they probably never had to. Now, of course, that doesn't mean that some scientists of the future may not find evidence of different kinds of senses in plants, but our present-day knowledge is such that we think that plants do not feel pain. Now, you've probably seen some of these Kirlian diagrams of leaves that have been cut cut, and then you put them on a photographic film, and you see that it's red, and you see things oozing out from the cut. And some people think, oh, gee, the plant is bleeding, it's in pain. Look at this Kirlian diagram. It shows you that there's a cut, and something is emanating from the cut. Well, that emanation is actually electrons that are leaving the surface of the leaf. It doesn't mean that the leaf understands or feels pain. It just means that it's an electrical signal, and that signal is more or less random, and that signal can be photographed in terms of what is called a Kirlian diagram. You've probably seen these diagrams if you put your hand on a photographic film and then develop that photographic film. You can see a ghost-like image of your hand with little sparks coming out. These are called Kirlian diagrams. It's not the aura that psychics talk about. It's nothing but electromagnetic radiation. Okay, well, let's move right along to the next listener phone call.
Hello, my name is Richard, and I would like to know why, when we talk about trying to accelerate something to the speed of light, it takes almost an infinite amount of energy. But photons, when we turn on like a flashlight, instantaneously reach or are traveling at the speed of light. How do we do this, or how does it happen? Thank you.
Well, to put it very simply, when objects move faster and faster, they get heavier and heavier. So M, the mass of an object, actually changes. The mass gets heavier the faster it moves, and that's why, as you mentioned, it would take an infinite amount of energy for a mass M to accelerate the speed of light. So how come photons are different? Photons are different because M is zero. The rest mass of a photon is zero. So let's increase zero. No matter how you try to double it, triple it, quadruple it, zero is zero. Because 0 times 10, 0 times 100, we all know that's zero. And so the rest mass of a photon stays zero even as it moves. And so photons obey a slightly different version of relativity because their rest mass is zero. Okay, let's move on to the next listener phone call.
Hello, my name is Tyler Gates, and I am a college freshman listening from Northern Arizona University. And I'm working on a research paper and would like to ask you on your opinion on whether you believe we will be able to travel to other solar systems within the next century. What materials, supplies would be needed? What would be the cost? What are the different possibilities of the travel, such as solar electric or nuclear electric propulsion? Thank you very much.
Well, you ask an interesting question that I addressed in my previous book, Physics of the Impossible. First of all, Stephen Hawking, my colleague, came out with a proposal this year to send postage stamp-sized chips to the nearby stars. That's a quick and dirty way to reach the stars without having to build the Enterprise and bankrupt the planet Earth as a consequence. A bank of laser beams generating 800 billion watts of power would energize a series of parachutes. Each parachute contains a tiny little chip the size of a postage stamp, and this parachute would then accelerate to 20% the speed of light. So it would take about 20 years to reach Proxima Centauri, the nearest star, and around that star there's a planet, an Earth-like planet that revolves around it. Now, is this doable? Yes. How much would it cost? $10 billion. When could it be done? Well, conceivably in a 20-year time frame. In reality, of course, it may never happen because, of course, who has $10 billion to throw around? But the point is that with off-the-shelf technology, within this century, it's conceivable that somebody may bankroll lasers that can inflate like a sail and go to Alpha Centauri. Now, in the next century, the 22nd century, new options emerge. Antimatter rockets, fusion rockets, atomic rockets, several different varieties of rockets have been proposed. And personally, I think that the ramjet fusion engine has a possibility. The ramjet fusion engine looks like an ice cream cone. It scoops hydrogen in the forward direction as it moves, burns it in a fusion reactor, and then it runs forever. Forever. you can attain any velocity you want as you approach the speed of light, up to the speed of light, because you can simply turn on the engine, and the engine scoops up hydrogen gas forever.
This is Science Fantastic. Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, we're going to throw the lines open because this hour is your hour. Okay, well, without any further ado, let's go right on to the first listener phone call.
Hi, this is Timothy. I was just wondering if we would be able to use Mars as a substation to reach the outer limits of space. Thank you.
Well, you ask a question that is one of the hot topics in NASA right now. As you realize, in the last 5 years, people criticize NASA for being the agency to nowhere, the agency that has nowhere to go, the agency that boldly goes where everyone has gone before. Well, last year, they finally laid out a sequence of events for the ultimate mission, the manned mission to Mars by 2030 at the earliest. The first stage is in 3 stages. The first stage of this 3-part mission to Mars would be to test the booster rocket and the payload, the Orion spacecraft. So in the first stage, they're going to continue testing of the SLS heavy booster rocket, sufficient to carry a manned crew to Mars, and the Orion spacecraft, which will actually house the astronauts. That's step 1. In step 2, they're going to go to the asteroid belt. They're going to pick a nearby target, perhaps a passing asteroid, and send our astronauts to perhaps land on it. And so we're going to be making the first extraterrestrial contact since the Apollo program of the 1960s. That's step 2. Step 3 is on to Mars. And of course, it's going to be an arduous process, perhaps 2 years, a 2-year mission to the red planet. And a number of stops in between. NASA has said that perhaps as going to Mars, perhaps a baby step would be to land on other asteroids and even the moons of Mars. Mars has 2 baby moons, Deimos and Phobos. They're probably asteroids which were captured by the gravitational field of Mars. We're not sure. And we hope to perhaps land on these because they'll act as a space station. In some sense, we already have 2 space stations circulating around Mars, Deimos and Phobos, the moons of Mars. And so some people think that perhaps we should land on them first before actually landing on the red planet. I should also point out that years ago, some Russian astronomers speculated that perhaps Deimos and Phobos, the 2 moons of Mars, were actually space stations built by Martians perhaps millions of years ago. And the reason for that, it's not so far-fetched. It turns out that if you look at the orbit of Deimos and Phobos very carefully with computers, you find that they deviate slightly from Newton's laws of motion. Now, if you deviate from Newton's laws of motion, you're in big trouble. It means that either Newton is wrong, which we do not want to believe, or perhaps something is tugging on you. Something is making you go in a slightly eccentric orbit. Well, now we have photographs, detailed photographs of Deimos and Phobos. And what do they look like? They look like a potato. They're irregularly shaped, they're pockmarked, and that perhaps can explain why the orbits are slightly wobbly. It's because of micrometeorite collisions. Because they're so small, they're pockmarked with meteor craters, and as a consequence, that might explain the reason why the orbits deviate ever so slightly from Newton's laws of motion. So anyway, to answer your question, yes, NASA has a sequence of events leading up to a manned mission to Mars, which includes visiting asteroids and perhaps visiting moons as a step toward going to the red planet. And I highly recommend you see the movie The Martian, because it is a science fiction movie that's devoid of aliens, devoid of UFOs. It gives you perhaps the most realistic sequence of what actually may happen in the coming decades leading up to perhaps 2030 or maybe 2040, when astronauts really do encounter the red planet. Okay, let's move right along to the next listener phone call.
Hey, love Professor Show, and my name is Chris. I wanted to say, I'm calling from Tampa, AM 820. Just wanted to say, there was a show, Lucille Ball was on, I believe it was Johnny Carson, and she claimed she picked up a radio station, a Japanese radio station, during World War II. And so that show called Mythbusters, they did about an hour-long program, and they proved with scientists and engineers that was impossible. You know, I don't know if you've ever seen the show Mythbusters. You know, they've been on for many, many years on, and they had proved on that show that was not possible to pick up a radio station with your teeth. So, it might be something you could look up on the computer. It was Lucille Ball, and she was on, I believe it was Johnny Carson. She claimed she could hear the Japanese talking and on her way to the studio to make movies and stuff. This was back in the 40s. And so anyway, the Mythbusters devoted, half or most of a show to proving that was totally impossible to pick up radio. Thank you.
Well, yes, I think a scientist would be a little bit skeptical as to whether Lucille Ball actually did pick up a radio message in Japanese. The first question is, how would she even know that it was Japanese? I mean, Japanese is not a language that you hear on television very frequently, especially back in the 1940s. So even if it was Japanese or maybe even another language, how would she even know? Second of all, it is true that the ionosphere, a sphere which surrounds the Earth, the outer layer of the Earth's atmosphere, has a propensity to bounce radio signals. In other words, over the horizon, radio signals can be heard by shortwave radio operators because the radio waves from on the other side of the Earth bounce off the ionosphere and will actually bounce several times before it comes to your shortwave. And so that's the reason why shortwave receivers can actually pick up messages from very, very long distances. But according to the story, Lucille Ball had an access to an ordinary radio. It wasn't a shortwave radio. But if it was a shortwave radio, then yes, it's true that radio waves will bounce off the ionosphere, making it possible for people to pick up messages all the way to Radio Moscow, for example. During the Cold War, I had a friend of mine who was an amateur shortwave radio operator, and he would listen to Radio Moscow and Radio Cuba, Radio Havana, regularly on his shortwave kit because of the fact that radio waves bounce off the ionosphere. Also, at different times of the day, you get better reception because the ionosphere itself is unstable. And as a consequence, certain times of the day, you can get signals much better than other times of the day. But to summarize, yes, I probably would doubt the fact that Lucille Ball actually did pick up Japanese, because how would she know that it's Japanese rather than another language? And because that she was probably not listening to a shortwave radio. Okay, well, moving right along now, let's take the next listener phone call.
Hello, my name is Ellie Jason. I'm from Buford, Georgia, and I want to know how stars shine.
Well, you ask a very important question. In fact, I'm positive that when young people are born, they're born scientists because we're born wondering, what does it all mean? Where do we come from? Why does the sun shine? Why do the stars shine? Well, if the stars shone because they are made out of coal or oil, they would have burnt out thousands of years ago. So oil and coal will not sustain a fire in outer space. Plus the fact you need oxygen. Without air, you cannot have fire. And so that's yet another reason why the sun does not use ordinary oil and coal in order to create heat. What the sun burns is hydrogen. And it burns hydrogen in a way that is totally different than the burning of paper or coal. It actually burns hydrogen by fusing, by smashing the protons in hydrogen together to form helium. So two hydrogens can be smashed together to create helium plus energy. And the amount of energy comes from Einstein's famous equation, E equals mc squared. In fact, I once read a comic book where the hero had emblazoned on his chest, E equals mc squared. So even comic book fans are familiar with E equals mc squared. So what does that formula mean? M corresponds to matter, turning into energy E very precisely by this equation.
Aha! Science fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The phone lines are open. Okay, well, moving right along now, let's take the next listener phone call.
Hi, my name is Clinton. I'm from Georgia. I have a question about batteries. Being that so many things take batteries nowadays, and batteries have been stagnant in their growth, what is the latest scientific theories for improving the battery? Thank you.
Well, you ask a very embarrassing question, because when we think of Moore's law and computer power, we believe that computers double in power every 18 months. That's right, every 18 months, every Christmas, your computer is almost twice as powerful as it was last Christmas, and that keeps the economy going. It thrills the public, and it's such a convenience to have so much computer power right at your fingertips. But we're spoiled. Moore's law does not apply to other things other than computer power. Most things grow in power linearly, like a straight line, rather than exponentially when computer power takes off like a rocket. So the same thing with batteries. Batteries grow at a glacial pace. In fact, it was 100 years ago, over 100 years ago, Thomas Edison and Henry Ford, who were good friends, had a bet. And the bet was, would the battery or gasoline emerge as the energy supply of the future? Well, we all know who won the bet. It was Henry Ford who won the bet. But ultimately, Thomas Edison may have the last laugh. Now, when you think of solar power and wind power, you say, well, everyone's been talking about that forever. Why don't we have cheap solar and cheap wind that can compete with fossil fuels like oil and coal? Well, there's a problem. The problem with solar is not the solar cell. The problem with solar and wind is storage, the battery. When the sun doesn't shine, when the wind doesn't blow, you're essentially blowing in the wind, and you're wasting your money. So that's one of the reasons why Henry Ford beat Thomas Edison. However, now that people are conscious about energy, engineers and inventors of all sorts are jumping into the battery game. This is something they should have done 100 years ago. They're jumping into the battery game to try to create more efficient and cheaper batteries. In fact, the price of batteries goes down about 7% per year. It's an astronomical rate just in the last decade because so many young enterprising people are jumping into this game. Now, even Elon Musk, the guy who is behind SpaceX, PayPal, and Tesla Motors, even he is backing batteries by investing in a huge project with Tesla Motors to create batteries that are usable for utilities. Just think about that. Your utilities waste energy when it's not peak summer or peak winter. But, of course, everyone demands that your power station be able to meet peak summer and peak winter electricity demands when demand is extremely high. But it's very inefficient to maintain that when it's not peak summer or peak winter. That's where these new batteries come in. These new batteries will smooth out this curve, creating efficiencies for the utility and also efficiencies for solar and wind power. And so there's no magic bullet. There's no exponential curve. There's no Moore's law for batteries. It's a slow, tedious process, fiddling, as inventors have always done, with better batteries.
This is Science Fantastic.
Great Scott. I know this is heavy.
You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Michio Kaku. The lines are open. Okay, well, without further ado, let's take the next listener phone call.
Yes, Professor, I'm a very, very big fan of yours all over TV and everything else. I've watched you for umpteen many times. But to be plain, pure, and simple to the, regular person that's not a PhD candidate in simple language, can you please describe Einstein's theory that you just went over, E equals mc squared, in the simplest form? And then another question I have to ask you, E equals mc squared, what if you take E equals mc squared times 3, multiply it with a factor? Okay, now will that go into a different dimension or something like that? I'm just curious. So thank you for your time, Professor.
Well, that dovetails with the previous question that we have about E equals mc squared. But many people think that E equals mc squared is the energy source that drives the universe. Think of the stars. Think of the sun. There's so much energy in this universe, and where does it come from? What is the engine that drives the universe? When a star explodes and releases so much energy that it lights up the galaxy, where does that energy come from? And it comes from Einstein's equation, E equals mc squared. Now, before Einstein, people thought that matter was matter and energy was energy. And there's no relationship between them. Heat, a light bulb, all that energy is different from a rock. A rock cannot turn into light. But you see, that's wrong, because a rock can turn into light if that rock happens to be made out of uranium-235, and that light happens to be X-rays from a nuclear detonation. So it is true that rocks can turn to light via Einstein's equation. Now, the key factor is c squared. M is mass, the mass of uranium or the mass of hydrogen. E is energy, but the key factor is c squared. C squared is the speed of light times the speed of light. That is an astronomically large number. Therefore, even a teaspoon of M can blow up all of New York City if you were to somehow release it in a nuclear detonation. And so even a tiny amount of M will release fabulous amounts of energy because c squared is such a large number. Now, you talk about tinkering with E equals mc squared. It turns out the E equals mc squared also holds in other dimensions. That's right. I work in something called string theory, which is defined in 11-dimensional hyperspace. And it turns out the E equals mc squared also works in other dimensions. So when you go to other dimensions, you do not multiply by an overall factor. You cannot take E equals twice mc squared or E equals 10 times mc squared. No, E equals mc squared. And that equation is actually true in other dimensions. However, I should also point out that we have absolutely no evidence that these other dimensions exist. However, the leading theory of physics, which is string theory, which is what I do for a living, we string theorists believe that there are other dimensions, in fact, up to 11 other dimensions. Okay, well, moving right along, let's take the next listener phone call.
Hi, Frederick Moore, KFQD, Anchorage, Alaska. My question was, the expansion of the universe is accelerating. Is there some unseen mass beyond the observable universe? Thank you.
Okay, well, unfortunately, we've run out of time in this segment, so we'll answer your question after the commercial break.
You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, before the break, we had a call. The call came in saying the universe is accelerating in its expansion, and what is causing it? Well, first of all, if I knew the answer, I would get the Nobel Prize in Physics. In fact, several years ago, 3 astronomers actually did win the Nobel Prize for showing that the universe is not just expanding, which even kids know by watching The Big Bang Theory on CBS television, but the universe is actually accelerating. Now, remember, every high school textbook that has a section on astronomy says that, well, yes, the universe is expanding, but it's probably slowing down, so there's probably not much to worry about. Well, we were wrong. The universe is not slowing down. The universe is actually accelerating and speeding up. Now, what does that mean? Does that mean that the universe is careening out of control and will eventually expand into nothingness? Well, we don't know. In fact, we don't even know why it's accelerating. The leading theory, and it's just a theory, the leading theory is that something is pushing the galaxies apart, and it's some kind of anti-gravitational force. We think it is the energy of nothing. It's called dark energy, which is the energy of nothing. Even nothingness, the vacuum, has some energy associated with it. And this term was actually introduced by Albert Einstein. It was Einstein himself who first contemplated the fact that even nothing has energy associated with it. But he eventually thought, well, no, maybe I'm wrong. Well, now we know that Einstein's, quote, biggest blunder, introducing the energy of nothing, is perhaps the single most important driving force of the entire universe. And we're clueless at the present time as to what it is. Now, the leading theory of cosmology is called string theory, which is what I do for a living. And string theory does give you an explanation of the expanding, accelerating universe, but it's not very satisfying. You have to put that number in by hand. It does allow for the acceleration of the universe, but the amount of acceleration of the universe has to be put in by hand. And many people think that that's a little bit unnatural. And so string theory at the present time has a big question mark when it comes to the accelerating universe. And so again, if you want to win a Nobel Prize in physics and have your name splattered all over the halls of science, then try to figure out what is driving the accelerating universe. In fact, if the universe keeps on accelerating, it means it's going to get awfully cold in the universe, and maybe some people think this could be the end of the universe, that the universe will expand so much that the sky will be totally black. We won't even be able to receive light from the distant galaxies, and it's going to be very cold as the universe continues to expand into nothingness.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open in this hour. Okay, well, moving right along, let's take the next listener phone call.
Thank you for taking my call, Professor. This is Charlie, Chattanooga, 102.3 FM. My question is, when you mentioned, I think it was about 10,000 years ago, that there were 2 miles of snow in New York, let's put it that way. When the snow is on there 2 miles thick, my question is the ocean down anymore, the level of the ocean? Thank you.
Well, you hit the nail on the head, and that is during the Ice Age, because so much water from the oceans was soaked up into the ice. It meant that sea levels actually dropped. And so the map of the Earth actually changed as a consequence. And this had consequences for North America. First of all, we think that most of North America was covered by about a half a mile of ice, and so it was really cold in most of North America. And we can see evidence of this in the Great Lakes. Why do we have the Great Lakes near Chicago and Michigan? We have the Great Lakes, so that's a remnant of the ice, half a mile of ice that melted 10,000 years ago. And so that means that the coastline of the world was much different. Now, when you take a look at what the map must have looked like, you see that there was a land bridge connecting Asia with Canada going through Alaska. And we think that many peoples, Asian peoples, perhaps in Mongolia, took advantage of that land bridge because sea levels were so low. It meant that it was relatively easy to cross from Siberia across Alaska into Canada, and they became the Native American peoples. In fact, by looking at DNA evidence, we can actually trace the lineage. We can actually see that there were at least 3, not just 1, 2, but at least 3 separate migrations from the old world into the new world that took place over 10,000 years ago during the Ice Age, because so much water was absorbed into ice that sea levels began to drop, changing the coastline so that Alaska expanded in size, making it possible for this land bridge to take peoples from Asia, for example, Mongolia, and we can now trace them going into the Americas. In fact, DNA evidence is so powerful that we can actually see migrations of Native Americans and Aboriginal peoples. For example, the Polynesians. Many people gasp realizing that the Polynesian people must have braved the Pacific Ocean in order to go to Hawaii. And by looking at DNA evidence, we know where they came from. Most Polynesian people came from Taiwan. Who would have thought? Who would have thought that Polynesian peoples are mainly Taiwanese people? In fact, I remember when I was a kid reading the work of Thor Heyerdahl, an explorer, who thought that explorers from Latin America sailed in the reverse direction and they populated Polynesia. Nope. We now have evidence from DNA by which we can actually trace island by island. We can actually see how the island hopping took place, and we can date it. We can actually give a date when each of the Polynesian islands was colonized by native peoples coming from Taiwan and going into the Pacific. Amazing. All of that from DNA analysis. Okay, well, let's move right along to the next listener phone call.
Hello, this is Keith McCabe from Hartley, Texas. I am calling you. I wrote you a letter. I hope you got it. I would like to ask you what you think of my idea of what string theory could be.
Okay, well, first of all, I have to apologize for the people who write me letters. I get hundreds of letters, and it's physically impossible to answer them, or else I'd be spending all my time plus sleeping time answering questions. So it's better for me to answer questions on radio, where I can actually interact with people directly. So instead of trying to critique people's theories, first of all, some people want to know, well, what is string theory? And so let me give you a brief description of string theory. First of all, when we split atoms apart, we find there are more particles. Hundreds, thousands of particles we get by smashing protons together with our particle accelerators. We give them bizarre names: leptons, hadrons, protons, neutrons, and all of them we think are nothing but musical notes on a tiny vibrating string. And so chemistry is nothing but the melodies we can play on these strings. Physics is the harmonies of these strings. And the universe we think is cosmic music, the music of vibrating strings.
Now, Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Okay, well, let's throw the lines open. Let's take the first listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
I was just curious of how the way that the dogs as in animals have evolved over the years. Did they come from wolves, or how did they all come about?
the different breeds, how are we mixing breeds and getting all these different variances of animals over the years? Thank you.
Well, you ask a very intriguing question that's being answered even as we speak by geneticists who are beginning to sequence the DNA of dogs. Well, first of all, we know that dogs were domesticated roughly 10,000 years ago. 10,000 years ago, that's when the Ice Age melted. We forget that before then, during the peak of the Ice Age, most of North America was under a half a mile of ice. Well, after the ice melted, agriculture gets off the ground slowly, civilization, villages start, and that's when we begin to domesticate dogs from the wolf, Canis lupus. And that's one reason why dogs of any breed can breed with any other dog, because they're all descended from one species, Canis lupus. Now, when scientists began to sequence the DNA of dogs, they found something very interesting. They found out that there was just not one branch of lineage, but several branches depending upon where you were on the planet Earth. So in other words, not once, but many times, different populations of people domesticated the dog and then began to breed the dog for their own particular purposes. That's why we have such a bewildering variety of dogs for specific purposes. Some dogs, for example, are good at shepherding sheep. Others are hunters. Others are simply good companions. That's why we have such a multiplicity of dogs. And dogs, of course, don't live very long. Dogs age much faster than us, about 5 times faster. So you can imagine how fast evolution has taken place, that we have bred the dog for just 10,000 years. Then you can even calculate roughly how many generations of dogs there have been since the very first dog. You just divide into 10,000 years. Now, not only this, but because dogs begin to be bred by humans and then we begin to interbreed dogs, that's the reason why dogs suffer from many genetic mutations. It's very sad. But if you have a dog, you begin to realize that as they age, they begin to exhibit many of the genetic mutations, their feet, their digestive system, cancers. They begin to show different kinds of genetic diseases because of all the inbreeding that took place. So in other words, man's best friend has in some sense paid a price. The benefit of domestication is that there are more dogs today than wolves. So from an evolutionary point of view, bingo. It was actually a success story for the dog because there are more dogs than wolves. But the price that dogs paid for this is that they are essentially riddled with genetic mutations, many of which begin to show themselves as they begin to age. Okay, well, let's take the next listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
My name is Eric, and I'm calling from Corpus Christi, Texas. 1440 Keys. And my question is, can we build, or have we already built, atomic-powered aircraft? I'm wondering if this aircraft could maybe describe what we've seen in the skies and don't have a true idea of what it is. And I'm wondering if maybe this might be the atomic-powered aircraft might be what we're looking at.
Well, Eric, you ask a very interesting question because my advisor, when I was young, starting in high school, was Edward Teller. Edward Teller was the father of the hydrogen bomb, and he was a very vocal proponent of putting nukes everywhere. Nukes not only to carve out canals between continents, but also nuclear power plants in aircraft carriers, submarines, rockets, and airplanes. So let me tell you a little bit about the secret history of this, which is rather interesting. interesting. Back in the 1950s, the United States military and government very seriously looked at the possibility of putting nuclear power plants, not just in submarines, which was a smashing success, but also in rockets and airplanes. In fact, there was a project called the Kiwi. The Kiwi is a flightless bird, and was aptly named because it was basically a nuclear rocket on a railroad track. So when you threw the switch, the ignition took place. All of a sudden, you had all this exhaust coming out one end, and the nuclear rocket would go barreling down the railroad tracks. Well, there was some problems. First of all, the reactor tended to be unstable. It tended to melt down. There were problems with maintaining the reactor, and the military eventually gave up. They said it's simply not worth it. For the cost-benefit analysis, they're simply not getting the bang for the buck. And the same thing for the airplane. It turns out that, yes, in principle, you could put a nuclear power plant in an airplane, and the airplane could go around the world many times. But simply refueling a jet, turned out to be much more cost-effective, not to mention the fact that if the rocket crashed or if the airplane crashed, you would have a nightmare. Can you imagine a nuclear power plant landing in someone's backyard? The contamination would be enormous. And in the 50s and 60s, the military had some experience with this because there were several broken arrows during that time. An arrow is jargon for a nuclear weapon. A broken arrow is a bomb that literally falls out of the bomb bay of a bomber. There have been a number of incidences where atomic bombs accidentally landed on South Carolina, North Carolina, off the coast of Georgia. And this, of course, was a huge embarrassment for the military. So we actually did have nuclear materials literally falling from the sky in terms of nuclear bombs. So, again, some people think that maybe, just maybe, flying saucer sightings are actually secret military craft. Well, who knows? We do know, however, that the military deliberately led the public to believe that sightings of the stealth bomber may in fact have been UFOs, to cover up the fact that the military was experimenting with stealth bombers, or bombers that can deflect and diffuse radar so they don't have much of radar signature. But basically, the reason why the atomic airplane was shelved was because it was not that safe, it was unstable, and basically not that cost effective. Simply refueling would give the range needed for airplanes to go pretty much around the world. Okay, well, let's take the next listener phone call. Hi, this is Science Fantastic. You're on the air. Any comments or questions?
This is Jessica from Corpus Christi. I'm listening to station 1440 AM. And my question is, who was the first person to think, like, okay, I'm going to eat whatever comes out of this chicken's butt? Well, basically I'm talking about an egg. But, like, who was that?
Okay, well, let me try to take a crack at that question. I think your question is in two parts. First of all, who was the first person to have a light bulb emerge over their head and say, oh, gee, that looks pretty delicious, an egg. Maybe I'll grab that egg. And then, of course, everybody wants to know which came first, the chicken or the egg. Well, let me take a stab at it. First of all, the first person to look at an egg and decide to eat it was probably not a person at all. We descended from the apes, according to the theory of Charles Darwin, and apes eat eggs. In fact, if you go even further back in time, mammals were once reptiles. Mammals, in fact, are an offshoot of the reptiles, and reptiles eat eggs as well. So the answer to your question is very simply, there was no first human who looked at an egg and said to themselves, well, gee, this is a great meal, because it goes back even before humankind was born. If you go all the way back, even primitive animals will eat eggs of other animals. And then the other question is, which came first, the chicken or the egg? And the answer to that is probably neither. The chicken and the egg probably emerged from a more simpler form you realize if you go way back into the past, now 2 billion years into the past, you just had microorganisms on the planet Earth that simply underwent mitosis, that is, splitting apart. It took billions of years for these germs, these bacteria, to create concrete organisms that then began to lay eggs and then began to differentiate. So to answer your question, there was no first human who spied the first egg. And which came first, the chicken or the egg? The answer is probably neither.
Science Fantastic. You're listening to Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, it's open mic. Okay, well, let's take the next listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
Hi, my name is Daniel Hensley, and I am calling from Pensacola, Florida. And I am talking from News Talk 1370, WCOA. My question is, spirits and everything, are they really matter? Like ghosts, can they actually become matter, or are they just like, is this like something of your brain? Is it like...
Okay, well, you ask a very ancient question that goes all the way back to the dawn of civilization. Take a look at any mythology from any society, and you'll see myths of spirits and ghosts and stuff like that. Well, as a scientist, we can only say a few things. Science is based on what is reproducible, measurable, and testable. That's the foundation of science. If you have a scientific result, it has to work all the time. It just can't work on Tuesdays or Thursdays, but not on Wednesdays. It has to be eternal. Well, when it comes to ghosts and things, we find a problem, and that is they're not reproducible. They're not testable. In fact, they're not even falsifiable. How can you prove or even disprove the existence of ghosts, demons, and spirits? So scientists are kind of at a loss at this point. However, that doesn't mean that some scientists haven't speculated about these things. So let's mention two possible speculations. One speculation, as you mentioned, is that they are perhaps figments of the imagination. Another is maybe they're from another dimension. If they're a figment of our imagination, then it turns out there should be a part of the brain which induces this kind of behavior. In fact, there is. It's called epileptic lesions. In fact, we've had guests on radio talking about this. It turns out that a certain lesion to the brain, a stroke, an injury, a blow to the brain, will actually set off these epileptic lesions, in which case you feel that you're in the presence of a spirit. Anything that happens, you think that something is behind it. These people, for example, when they're interviewed in hospitals, say that when it rains, it's because there are evil spirits that are punishing you. That if you fall down, it's because you did something bad that day. So any event that happens, there's intentionality, evil, or a spirit behind it. And you can even induce this with radio. It turns out there's an electromagnetic transmitter. Time Magazine even did a story on it, where if you shine this radio to a certain part of the brain, you can actually induce this effect so that you feel like you're in the presence of a ghost or a spirit. Richard Dawkins, who I met a few months ago in Mexico at a conference, he's an atheist from Oxford University, a leading atheist, so some people had the bright idea of putting him in this contraption. So they put radio waves into his brain to see whether or not this confirmed atheist would say that, yes, there is a God. Well, after Professor Dawkins came out, he said, nope, I didn't see any ghosts at all. However, there is another theory that says that maybe ghosts are from another dimension. Let's say that you have a tabletop where there are people living on a tabletop, flatlanders that are squashed in two dimensions. If you are standing above the table looking down, then the flatlanders cannot see you. You are invisible, but you could perform all sorts of magic tricks. You could put your finger right through the table, the surface of the table, and the beings on the table would see a sphere, a circle of flesh as you stick your finger in it. you'd be able to peel these people off the table and make them float, so they would disappear off their universe, and you can put them back. So in other words, if we are nothing but flatlanders living in a flat universe, then somebody from a higher dimension could disappear, reappear, reach into our stomach, perform surgery without cutting our skin, and do all sorts of magic feats that are usually associated with ghosts. Well, I don't know. All I'm saying is that theologians have written about the possibility that maybe ghosts live in a higher dimension. Many of my books, like Hyperspace, talk about the lore that goes back. But, hey, I'm a scientist. I won't believe it till we can reproduce it in the laboratory.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, once again, it is open mic. Okay, the lines are open, so let's take the next listener phone call. Hello.
Jim Sanders, Pensacola, Florida, listening on WCLA Radio 1370 AM. If the Big Bang happened 13.5 billion years ago and things are rushing away from that point, then isn't there a whole lot of nothing between that point and the edge where we are expanding away like a big bubble?
Okay, well, you ask a question that a lot of people ask when they first hear about the Big Bang Theory. If the Big Bang means that eventually we came from a point, and we are 13.7 billion years away from that original point, then first of all, where is that point? Is it in the constellation Virgo, the constellation of the Big Dipper? Where is that point? And are we spinning away from that point at a very fast velocity? And as you point out, is there a gap? Well, think of a balloon. Think of a balloon, and we are like flies on flypaper. We're trapped on the surface of the balloon, and the balloon is expanding in all directions. Okay, got that. Now, if you ask, let's say, an ant walking on the surface of this balloon, where did the balloon originate from? Where was the original expansion taking place? Well, the ant would say, well, nowhere. Nowhere on the surface of the balloon did the expansion take place. The balloon is expanding away from the point of origin. So, in other words, the Big Bang, in some sense, happened everywhere and nowhere. There is no point on the surface of the balloon that is the origin of the Big Bang. So, if you ask the ant, then where did the expansion take place? The answer would be, well, it's off the surface of the balloon. But since the surface of the balloon is everything there is, the whole universe is the surface of the balloon, then the Big Bang took place off the surface of the universe. In other words, in hyperspace, in another dimension. So that's the simplest way to realize that you cannot point to one particular point in the night sky and say that's the point of the origin of the universe. So if you were around 13.7 billion years ago, what would you see? Back then, the universe would be very small, smaller than a bowling ball, smaller than a ping pong ball, smaller than an electron. And as it expanded, you would ask a question, well, where is the Big Bang? And the answer would be everywhere. Everywhere you look, you would see radiation. It'd be very hot, quite radioactive. Everywhere you look, you would see essentially the origin of the Big Bang. Now, you may say to yourself, if it's that abstract, then how do we even know it's correct? Well, we have photographs of the Big Bang. Pictures, baby pictures of the infant universe. Go to nasa.gov. And look under WMAP, W-M-A-P. That's a satellite which is photographing the explosion itself. Believe it or not, the explosion is still reverberating around the surface of our balloon. So let's say the balloon is expanding, but there are ripples on the surface of the balloon because the origin was so violent that it created shock waves. Well, we can photograph these shock waves, and by golly, it looks like an explosion. This is called the famous microwave background radiation. The radiation of the Big Bang is quite cold now. It's in the microwave range, 3 degrees above absolute zero, and you can photograph that radiation. And in fact, when you have a radio or TV and you get that static on your radio, some of that static actually comes from Genesis. So believe it or not, you are actually listening to creation itself. The static, that buzz you hear on radio, some of it comes from Jupiter. The planet Jupiter emits a lot of radiation, but a lot of that radiation also comes from the origin of the universe itself. Okay, I think we have time for another listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
Jonathan, I am calling from Inglewood, California. I'm listening to you on Freedom 970. And I don't think that time exists. Can you tell me whether or not you believe it does?
Well, some people say space, time, maybe it's all an optical illusion. Maybe time doesn't really exist. Maybe space doesn't exist. Well, that's when we have to define things, because without definitions, we're just spouting words into the vacuum. And, when you define time, you realize that time is a way to measure change. When things change, we need a way to measure that change, and we call that time. So obviously things change. The very fact that you could even ask that question is a consequence of the fact that your muscles can move, your mouth can move, and the radio waves can go across space, and I can listen to it. So the very fact that there is change means that there is time, because time is nothing but a way that we have of measuring change. Now, Shakespeare, I think, had the best way of looking at it. Shakespeare said that the universe is a stage. Everything around us is nothing but a stage. And we are actors making our entrances and exits on the stage of life. Well, this stage is space. We are matter propelled by energy. And the way in which you measure change along the stage of life is time. Now, of course, things get very complicated when Einstein comes along, and he shows that there's really a four-dimensional structure, that is, space and time are really, in some sense, part of a single fabric, a fabric that can stretch and bend. So, in other words, not only is there time, but there's also space, and that space and time are part of a larger entity called space-time. Matter and energy are also part of a larger concept called matter-energy, and that's the relativistic way, the Einsteinian way of viewing the universe.
This is Science Fantastic. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Well, let's take the next listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
Hi, this is Steve. I'm calling from Tucson, Arizona. I know that hair on our body is essentially a dead organism. When you cut a hair, there's no nerve. Yet hair seems to know how long to grow. The hair on my arms does not grow as long as the hair on my head. If I shave the hair on my arm or leg, it only grows back a certain length. How does the hair know how long to grow? Thank you.
Well, Steve, you ask a very interesting question, which had enormous commercial implications because, of course, as baby boomers age, they lose their hair, specifically on the top of their head. And so baldness is going to be one of the targets of biotechnology. In fact, recently it was announced that we're unraveling some of the genes of baldness, and that in turn could give us real, not fake, but real cures for baldness. Well, first of all, let's talk about what is hair. Hair, believe it or not, is protein. As you pointed out, it's not alive in the usual sense of the word. It is protein, not the kind of protein that builds muscle, but nonetheless a form of protein. And hair, left to itself, will simply grow infinitely long. There are certain peoples who don't cut their hair, and their hair grows on to be very long. But hair also falls out, and that's why certain hairs on your arm and places like that don't simply get longer and longer. It's not that the hair suddenly shuts itself off. The hair falls off, and new hair grows, and it gives the illusion that the hair suddenly knows when to stop.
Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Okay, well, let's take the next listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
My question is, why can't NASA use old technology that's been proven from the 70s and a design that is ultra safe and ship some of this nuclear waste out towards the sun, charging, of course, the nuclear power companies a high premium, not only in America, but in France, in Germany, and where they're having all these problems with the nuclear waste, make their own money and therefore turn that money over and fund missions that they would like to run but can't because they can't get money from the government.
Well, you ask a question that actually has some very deep answers to it. At first, it sounds like a no-brainer. Nuclear power plants generate nuclear waste, so why not simply send it to the sun? The sun is the ultimate garbage can, right? Well, there are some very big practical problems which have prevented this from happening. First of all, booster rocket failure takes place about 1% of the time. That's right. When our brave astronauts don their spacesuits, they know that 1% of the time they may not come back. These are former fighter pilots, former military people. A lot of them know the risks of going into space. If you calculate the number of disasters, for example, on the space shuttle, we've had 2 horrendous accidents, each one killing 7 brave astronauts, then the odds came out pretty much right on the dot. 1% of the time. 1% of the space shuttle shots and ended in tragic failure. Now, you can imagine what would happen if nuclear waste were on one of these rockets. Sure, you're right. Many of the shots would go to the sun. We can do that. So you say to yourself, well, why not send all the waste into outer space? Well, there's several problems. One, of course, is booster rocket failure. 1% of the time, as Isaac Newton said, what goes up comes back down, usually on somebody's backyard. And the ecological implications of that would be horrible. Can you imagine a Chernobyl from outer space spewing all the radioactive waste? But there's also a more mundane, practical problem, cost. It costs about $10,000 to put a pound of anything into orbit. Forget going to the sun. We're just talking about spinning wheels around the Earth. $10,000 per pound. Get on a bathroom scale and weigh yourself. Well, if you're made out of solid gold, if your body were made out of solid gold, that's the cost of what it would take to put a pound, to put your body into orbit, $10,000 a pound. Now, to send it into the sun would cost more like $100,000 a pound to send it into the sun. So you see, there's some real problems with regards to cost. And then, of course, you have the other problem, the sheer amount of nuclear waste. Every reactor produces about 30 tons, not pounds, 30 tons of high-level waste per year. And the United States alone has about 100 reactors. So do the math. 100 times 30 tons per year, and you realize the enormous amount of nuclear waste just generated by the United States alone. And France, hey, something on the order of 70% of their electricity in France comes from nuclear power. So you know that the French have an even larger commitment to nuclear energy than us, and that means an enormous amount of waste. And how long do we have to guard it? tens of thousands to millions of years. That's incredible. The half-life of uranium-238, for example, is 4.5 billion years. That's the age of the solar system. The age of the solar system is the half-life of uranium-238. Now, by law, the United States government has stated that radioactive waste should be sequestered from the environment for 10,000 years. That's why in Yucca Mountains outside Las Vegas, we were going to put our nuclear waste. But the Yucca Mountain site has been canceled by President Barack Obama. Why? It's unstable. 10,000 years ago, we had an ice age, for God's sake. An ice age. How do you predict these things? How can you make sure that nuclear waste does not encounter ice and flooding over a 10,000-year period of time when the last 10,000 years, most of North America was under a half a mile of ice? Well, the headache proliferates on and on. Now, we physicists have thought about all these things. There's even an issue of the Journal of Modern Physics, which goes to the options. Another option was to put it under the seabed, inject it directly into the tectonic plates. Well, that sounds like a great idea. Tectonic plates are stable for millions of years, so why not simply shoot the waste beneath the plates? Well, the conclusion of physicists was that we know not that much about earthquakes and the surface of the Earth. We know even less about the bottom of the ocean. So injecting nuclear waste on the bottom of the oceans would be a nightmare with unpredictable results. Yet another possibility was shoot it in salt domes. Well, we tried that in Lyons, Kansas. Kansas was supposed to be the site where we would put nuclear waste, but then it turns out that we didn't know that the Lyons, Kansas was used by wildcatters, and there's like holes drilled by them that have unknown locations. It's like pockmarked, like Swiss cheese. Well, as you can imagine, for all these reasons, we simply don't know what to do with the waste. Well, unfortunately, that's it. Once again, this is Science Fantastic with Professor Michio Kaku. Good day.